Hello my dear students. So this network analysis is a very basic course for electrical engineering students as well as electronics students. Okay, this network analysis course consists of analyzing the different complex networks and reducing the network with using the different techniques. Okay, so before we start, first let us know what is the objective of the network analysis course. So the objectives of this course is to study Kirchhoff law, voltage and current law, especially these two, and to reduce network by applying a source transformation, to convert star delta and delta to star networks, to analyze the given network and find loop current and node voltages. These are the objectives which we set for the module 1, and the outcomes of this module 1 is understanding the Kirchhoff laws, reduce the network by applying source transformation, convert star delta to star and analyze the given network and find loop current and the node voltages. So what are the contents that we are going to cover here is source transformation, source shifting, star delta transformation, dependent independent sources, mesh analysis and node analysis. Yeah, this is a basic concepts that we are going to cover, and we have to learn about a few basic terminology. Most of the terminology you have already learned in the 12th, but still we once again will repeat so that you will have a continuation of that knowledge and you will remember the terms. Okay, so first is defining the network theory. So this network theory is the study of solving the problems of electric circuits or electric networks. So we are going to see what are the electric circuits and what are the electric networks in the next slide. In the network theory, we will frequently use some of the terms, especially electric circuits, electric network, currents, voltage, power, etc. So what is an electric circuit? An electric circuit contains a closed path for providing a flow of electrons from voltage source or from a current source. The elements present in an electric circuit will be in either in the series or in parallel, or it can be both. Okay, the combination of series parallel circuit. Okay. Next comes electric network. An electric network needs to contain a closed path for providing a flow of electrons from voltage source to voltage source or a current source. So sometimes this electric circuit and electric network terms can be interchanged. Okay, so we can just conclude that all electric circuits are electric networks, but it is not true for the reverse. Okay, so next term is current. The current I, we always denote the current with the alphabet I. So the current I flowing through a conductor is nothing but the time rate of flow of charges. Okay, and this current can be mathematically written as I equal to dq by dt, where q is the charge and it is expressed in coulombs, and t is the time and it is expressed in seconds. Next term is a voltage. It is usually denoted by V. It is nothing but potential difference between two terminals. Okay, so it is also sometimes referred as that potential as electromotive force which causes the charge to flow. So mathematically we can express that voltage is equal to dW by dQ, where W is the potential energy and expressed in joules, and Q is the charge and it is expressed in terms of coulombs. And the power denoted as P is nothing but the time rate of flow of electrical energy. Mathematically it can be expressed as dW by dt. Okay, where W is the electrical energy and we express already this is in joules. Okay, and we can rewrite the other expressions for P as P equal to dW by dt, and we know dW by dq into dq by dt, which is nothing but a Vi. So types, coming to the different types of network elements. So we come across different types of networks. So in that we can majorly classify these networks and as active network or passive network. That depends on the elements used in the active on elements or passive elements, and further networks can also be classified as linear network or non-linear network. Again, it depends on the elements used in that network as linear elements or non-linear elements, bilateral elements and unilateral elements. So when we use these elements in a network, so that network can be called as a bilateral network or unilateral network. Coming to the active elements and passive elements. So we can classify the network elements into either the active or passive based on the ability of the network to deliver the power. If a network is having the ability to deliver the power, we can classify that as a active network. So in that network, we will find the active elements which delivers the power to other elements and which are present in a electric circuit. Sometimes this may absorb, okay, even these active elements can absorb the power, okay, like the passive elements, but still we call that if it is present in a network, this network, the active elements is present in a network, we call that as a active network. Okay, for example, we have a voltage source and the current source. If in a network voltage source and current source are present, then we call it as an active network. Coming to the passive network, which includes the passive elements. So this passive, as the name suggests, is just passive. It doesn't have a ability to deliver the power. It just absorbs the power. Okay, sometimes this power can be dissipated as heat, or it can also store this power in terms of energy, okay, in the form of magnetic field or electric field. For example, if the element dissipates the power in terms of heat, that element we referred as a resistor. When the element stores the energy, we referred it as a inductor or capacitor. Okay, this is the classification of the active network and passive network based on the elements which are active and passive. Now, we'll move on to the next type of network, that is linear network and non-linear network. When the linear elements present in a linear network, we call it as a linear network. When non-linear elements present in the network, we call it as a non-linear network. Okay, so here, what are the linear elements? So these are the elements that show a linear relationship between the voltage and the current. Okay, so if in a network or any electrical circuit, if there exists a linear relationship between the voltage and current, then we call that as a linear network. And this is possible when the network includes the linear elements. So what are the linear elements? For example, resistors, inductors and capacitors. Okay. Similarly, non-linear elements. So these are the elements which does not show a linear relationship between the voltage and current. For example, voltage source and the current sources. Next comes the bilateral elements and unilateral elements. So when the network is classified based on the direction of flow of current, okay, then we call it as a bilateral network or unilateral network. So in the bilateral network, we find the bilateral elements. Okay, so what are these bilateral elements? Bilateral elements are the elements that allow the current in both the directions, forward direction as well as in the reverse direction. So it will allow the current to flow in both the direction and it offers the same impedance. Okay, so when the current is flowing from A to B, it will offer the same impedance Z. Similarly, when the current flowing from B to A, the impedance will remain as a Z only. So if that is the case, okay, so you find in the network, then we call that network as a bilateral network. Okay. Similarly, unilateral network. So unilateral network which consists of a unilateral elements, and in this the current this network will allow the current flow only in one direction, because if it starts flowing from B to A, then the reverse direction, it will offer the different impedances to that. Okay, so impedance will change depending upon the direction of the flow of current. So in that case, we call it as a unilateral element. Lumped network and distributed network. So lumped network, as the name suggests, all the network elements are physically present and it can be separable, okay, physically separable. Say suppose if we have a network connected in a breadboard, you can remove the resistors, okay, and the sources we can remove. So this type of network we call it as a lumped network, okay. And distributed network, here the network elements are present, but the elements value or the quantity will be distributed throughout the network. It is not physically separable. The elements cannot be separated in this network, okay. So this type of network we call it as a distributed network. For example, transmission lines. So we have already know about the voltage and current. Let us consider the next terminology, that is branch, node, loop and mesh. So what is a branch? A circuit element connected between two terminals, usually in series actually. So this we call it as a branch. When two or more branches connected together, okay, the common point of this branch we call it as a node, okay. And loop is a closed path, okay, closed path of the current flow, you can say, that we call it as a loop. And mesh, it is also a loop, but it doesn't contain one more loop inside that, okay. So the very basic loop we call it as a mesh, and two or more mesh we call it as a loop. Now comes the energy sources. So before reducing any network, we should know what are the sources we have, whether it is an ideal source or it is a practical source, whether it is dependent source or an independent source, okay. So first we will see what is the independent source. So these independent sources produce a fixed value of voltage or current, okay, and irrespective of the elements connected to that. That means you can connect n number of elements, but its value is only fixed. So its value is fixed even if you connect 100 resistor to this terminal. So the source Vs, okay, that source will give you the only fixed value, okay. So this type of sources we call it as a independent source, which is independent of the element connected to that terminal of the source, okay. So we find two types of independent source depending upon the what it is offering, okay. Independent voltage source and independent current source. Independent voltage source is symbolized as this Vs. You will have a plus and minus sign which symbolizes the independent voltage source. Independent current source, you have a arrow mark here, okay. So this arrow mark symbolizes that it is a current source, okay, connected between two terminals, okay. This is about independent ideal sources. When it comes to the practical sources, we find voltage source is followed by a resistor. In the practical sources, so this is your ideal source. So when it comes to the practical source, especially in the voltage source, it will followed by a resistor. So if this is the case, then we call it as a practical source. Similarly, in the current source also, this is the ideal source. If it is connected in parallel with the resistor, then this combination we call it as a practical current source. You can see the response of the voltage and the current for the practical sources, okay. So in the ideal, the irrespective of the elements present in the network, the value of the Vs is fixed, whereas in the practical, it depends on the elements connected and it can vary with respect to the ideal source. Similarly, current source also. So we know what is the independent source. Now we'll come to the dependent source. So what is the dependent source? So as the name suggests, dependent sources produce the amount of voltage or current depending upon the other voltage or current present in the network. That means dependent sources are also called as a control source. Dependent sources can be further classified, okay, based on the dependent voltage source and dependent current source. So dependent voltage source produces a voltage across its terminal. Okay, the amount of this voltage is dependent on some other voltage or current present in the network. Okay, suppose if I have a 5 volts in the network and the dependent source which depends on the 5 volts source, then the value of the dependent source will vary depending upon the network elements. Okay, similarly the current source, dependent current source. So this dependent voltage source can be again further classified into two categories: dependent voltage source, and dependent current source. Okay, current dependent voltage source, voltage dependent voltage source, current dependent voltage source and voltage dependent current source. Coming to the current sources, the dependent current sources produces a current which based on the depend on the voltage or current in the network. Okay, so this again it is classified as voltage dependent current source and current dependent voltage source. Then comes first technique in the reduction of the network. We'll see the source transformation. The technique, this source transformation is used for the transforming the network, or you can say the reduction technique. Okay, so the technique of transforming one source into another is called as a source transformation technique, and this follows the two possible transformation. One is practical voltage source into a practical current source. We can't transform the ideal sources to one form to another form, but we can do the practical sources. So we can transform the practical voltage source into current source and current source into voltage source. We'll see one example here. Here there is a practical voltage source. Okay, the current in this voltage source will be given by I equal to Vs by Rs. Okay, so from that we find the current, and while transforming we can just write the resistance, whatever the resistance which is present in series with the voltage source, we will connect that as a parallel with the current source, and the calculated current, that is equal to Is equal to Vs by Rs. This value of the source will connect across the resistor, and this forms the practical current source. So this forms the practical current source which is get transformed from the practical voltage source. Similarly, when we take up the practical current source, okay, so practical current source will have a current element and as well as the current source element and as well as the resistor connected in parallel to the source element. Okay, so this can be transformed into a voltage source. We know the formula V equal to I into R. Okay, so we will calculate for using this formula. The same value we will connect here, and the resistance which is connected across the current source will connect as a series in the network. Okay, this is how we will transform one practical source to another practical source. So before we use any kind of network reductions, we should know these three laws, very basic law. One is Ohm's law, Kirchhoff voltage law and current law. So what is that Ohm's law states? For a given, that is temperature remaining constant, that means temperature when it is remains constant, the current flow through any conductor is directly proportional to the potential difference between the ends of the conductor. So what it says, so when we have two ends of the conductor, let us name it as A and B, keeping the temperature T as constant. Okay, so the current flow in the conductor, okay, through any conductor is directly proportional to the potential difference between the terminals of the conductor. So I current flowing through this conductor from this point to this point is directionally proportional to the voltage, and the constant of proportionality, okay, so constant of proportionality is nothing but impedance. Okay, the constant of proportionality is nothing but impedance. Okay. If this impedance is purely resistive, then we can write V equal to I into R. Okay. So this is Ohm's law. Next comes to the Kirchhoff voltage law. So what is this Kirchhoff voltage law? It states that algebraic sum of all the branch voltages in any closed loop of a network is 0 at all instant of time. So what is that means? It's sum of all branch voltages. This is one branch. Element connected between two ends is one branch. Okay, and this is another branch, this is another branch, and this one is another branch. Okay, so when we see the branch voltages, voltage across this, let us consider the voltage across this as V1 and voltage across this as V2. Okay, and as this V3 from this point to this point P4. Okay, so sum of all these voltages starting from V1, V2, V3, V4, but you can see the direction of the flow of the current. Okay, so here it is in the positive direction. So here minus to plus it is going. So this source will become minus. So voltage source will become minus. So sum of this will be equal to 0. Algebraic sum of this voltage will be equal to 0 as per the Kirchhoff law. Again, Kirchhoff current law. This is also called as conservation of charges. Here it says that algebraic sum of currents into a node is 0. So whatever the current coming into the node and going out to the node, so going out of the node, so these two currents, okay, so these currents will be, the sum of these currents will be 0. So we'll follow the sign convention here. So plus sign we will include for the current if it is into the node, and minus sign if it is going away from the node. I repeat. So current, if it is coming into the node, will assign a plus, okay, and current going outside the node will assign a minus. So when we see this picture, what are the current which is coming into the node? This is the node. Okay. So this entering the node, this is also entering the node, okay, and this are leaving the node. So sum of this will be equal to entering the node, as I told, it is plus I1 plus I4, leaving the node minus I5 minus I2, and you have one more current source here, current which is coming into the node, that is I3. So sum of all these currents to the node at the node will be equal to 0. So branch currents at the node will be equal to sum of branch currents at the node will be equal to 0. This is the Kirchhoff current law. And one more thing you need to know while solving the problems in the network analysis. One is voltage divider rule, another is current divider rule. What is this voltage divider rule? The voltage dropped across a series resistor is directly proportional to its magnitude. We know that any voltage drop across a series resistor is directly proportional to its magnitude. The voltage divider rule lets us to calculate the voltage drop across a resistor that is connected in series to the other resistor. So for example, in this network, this resistor and this resistor are connected in series, okay, and if I wanted to find out what is the voltage across this resistor, so voltage across this resistor will be Vx equal to Rx by total resistor. The total resistor is nothing but R1 plus Rx. So where R1 is the series connected resistor with respect to this Rx and into Vin. So this will be the voltage across Vx. Similarly, if I wanted to calculate what is the voltage across R1, then I will calculate it as V1 will be equal to R1 divided by RT into Vin. V1 will be equal to R1 divided by RT into Vin. So this is how we will calculate the voltage across any element using a voltage divider rule. Then comes the current divider rule. So whenever the current has to divide, okay, among the resistors which is connected in parallel, we use this rule, which is given by, say suppose if I wanted to calculate the what is I1, that is current flowing through the resistor R1, given that Is is the current flowing into the network from the source Vs, then I1 will be equal to R2 divided by R1 plus R2 into Is. Similarly, we can also calculate what is the current flowing into the R2, which is another branch, okay. And then I2 will be equal to R1 divided by R1 plus R2 into Is. So this is the current divider rule. Next, combinations of sources. Okay. So voltage sources which can come in series and it can be replaced by a single source. So for example, you have a V1 and V2 which is attached in series. So since the direction of the current flow, it will be like this, from the negative to positive. So you both can be combined. The values of these two sources can be combined and assigned to a single source. So that is possible. Suppose if I have voltage source connected like this. Okay. So this is V1 and this is V2. Let us say V1 is greater than V2. Then we can replace this source with the node A and B. Let us consider the terminals. So this can be replaced, since V1 is greater than V2, replaced with a single source as V1 minus V2. Why minus? Because the polarity is opposite in the second source. So V1 minus V2. So V1, since we have taken that as a greater than V2, so this will be V1 minus V2 across the same terminal. Okay. Suppose V2 is greater than V1, then check out the polarity what I am writing here. So for this one is V2 is greater than V1. So I will write the resultant V will be equal to V2 minus V1 across the A and B. Okay. So we can replace n number of voltage sources connected in this fashion in series, can be replaced with one single voltage source. So current source can also be replaced, n number of current source can also be replaced with a single source. Okay. So that is by like when it is connected in parallel, and if both the current sources having the same direction, we can just add this one. Suppose if the current source I1 is in this direction and I2 is in this direction, then the resultant, let us consider this is A and B, or shall I? Okay, so two sources are connected like this. This is I1, this is I2 across two terminals A and B. The resultant, okay, source will be I1 minus I2, which is equal to Ix. Let us consider this as Ix. Okay, so when we can take, when I1 is greater than I2. Similarly, this will be equal to I2 minus I1. Okay, considering I2 is greater than, the value of I2 is greater than the I1. Okay, I hope you have understood the combination of sources. Let us move to the next section, redundant elements. Okay, sometimes in a network, even though if it is not required to be connected, okay, it will be present in the network, we have to identify such elements and we can neglect that for our analysis. Okay, so for example, the resistance or impedances connected in series with the current source is called as a redundant resistance or impedance. So for example here, so current source is connected with the resistance. Okay, the resistance will become a redundant. Even though if it is not present, the current value will be the same. Okay. Similarly, voltage, the resistance or impedance connected across any voltage source, especially ideal voltage sources, then we call this as a redundant. Okay. So the value remains the same even if you remove that resistance. Okay. Resistor from the network. Similarly, when you have a current source and a voltage source both together in series, so voltage source will become a redundant for that terminal. So we can replace these two sources with a single source, that is only your current source. Okay. So these are the redundant elements which may be present in the network and you need to identify before proceeding to the analysis. Okay. So now with whatever we have studied so far, with that knowledge we will solve a few problems. Okay. So this is the problem based on the source transformation. First, identify whether this source network, sources present in the network are ideal or a practical sources. Okay, how to identify ideal and practical sources? I'll just repeat that. If you have ideal source, so if it is current, it will be like this. If it is voltage, resistor will be missing in that. Okay. Similarly, in the practical source, current source will have a resistance connected in parallel and voltage source will have a resistance connected in series. So identifying this before we solve the problem. So once we identify, we will get to the solving the problem here using the source transformation. So this problem will consists of a current source of 10 amps and connected with the resistance 2 ohms and voltage source 12 volts, and another current source which is in the opposite direction with respect to that is 2 amps connected with the 4 ohms resistors in parallel to that, and we have one more current source, that is 2 amps connected between the two terminals. So what is the question? Reduce the network shown there below into a single voltage source between the A and B. So we have to connect a single voltage source which will include all the characteristics of these elements between the terminal 1 A and B. Okay, we'll start with the process. So terminal A is connected with the current source, and here you can see when you look at only this section of the network, it is a practical current source. Okay, so practical current source, how we will transform into voltage source, practical voltage source. So V will be equal to I into R. So voltage source we will connect. What is the value of the voltage source here now? V1. Let us consider it as a V1 voltage source. V1 voltage source will be equal to 10 into 2, which is equal to 20 volts. Okay, so this source will become 20 volts. So after connecting this voltage source, next we have to connect whatever the resistors which is across the current source. That resistor should be in series with the voltage source. So let us consider. So what is the resistor? This is 2 ohms. So now we have transformed the practical current source into a practical voltage source using source transformation. So next we have another source here, which is also a voltage source. We will retain that. Okay. Again, we will transform this current source into a voltage source. So let us consider this voltage source as V2. So V2 will be equal to, what is high? It is 2 amps. What is the resistance? It is 4. So it will be 8 volts. Okay. And what is the direction of this voltage source? Here you can see the arrow mark goes up. So the direction of the polarity of the voltage source will be plus and minus. If the arrow mark goes down, the direction of the voltage source polarities will be minus and plus. Okay, so this you remember. First comes minus, then plus. So wherever there is an arrow mark, towards that you should have a plus polarity. Okay, positive polarity. So this V2 is now 8 volts. Okay, so this is connected to one current source, that is 2 amps between the terminals A and B. Okay, so now we will add all the sources. Oh, okay, one more thing, that 4 ohms should be in series with this source. So I'll just connect it here, 4 ohms. Okay, so now this current, so practical current source is transformed into a practical voltage source. So all the resistors I will rewrite and summarize this as 4 ohms plus 2 ohms. So I'll add up these two. So this will become 4 plus 2, 6 ohms resistor. Okay, and this 12 volts plus 20 volts, both are having the same polarity. So this will be 32 volts. Okay, 32 volts. 32 volts is in series with the minus 8 volts because it is having the opposite polarity as that of the major voltage in this branch. So 32 volts minus, okay, let us write this one. We'll split that. How we got this 32? So 20 volt source. This is 20 volt source. This is 12 volt source. Okay, this will be the 8 volt source. So resultant of this will be 20 plus 12, 32 minus 8. How much it will come? And we have to, one more thing we have to see. So when we are doing this one, we have to see the polarity. So this 2 will have a greater value compared to the 8. Okay, 32 is greater than 8. So the polarity of the 32 volts will be retained in the resultant circuit. Okay, so polarity of the 32 is plus and minus. So it will come around 24 volts. So once again, this will be connected in parallel with the 2 amps current source between the terminal A and B. Okay. Now further we have to reduce this one. For that I will just erase this. So we have this circuit. So this will be again transformed into a voltage source. So for that, first, before transforming the voltage source, since no resistance is connected across this terminal in this branch, so this will become an ideal source. So ideal source we can't transform, only practical source only we can transform as per the rule. So this voltage source, practical voltage source, will transform into a current source. Then we will again come back to the reduction. Okay, so the next step will be voltage source to current source. Okay, so in order to do that voltage source to current source, we have to find out what is the current. Current will be equal to V by R. Okay, what is V? V here is 24 divided by 6. You have a 4 amps current. So you need to connect 4 amps current with the polarity and the direction of the current source. You just check it. This is 4 amps. And what about the resistor? Resistor should be connected in parallel to this source. And what should be the resistor value? Resistor value is 6 ohms. Then you have one more source which is 2 amps connected between A and B. Okay. So again further we'll reduce this one into a voltage source. Okay. So you can see this source and this source are having a opposite polarity. So the resultant source will have the greater, whichever the greater source will have, the same polarity will be retained, or same direction of the current will be retained. So 4 minus 2 will be again 2 amps pointing upwards, because 4 amps source is greater than the 2 amp source. Then you have 6 ohms resistor connecting to that. This is the reduction of the entire network into a practical current source. What is the question actually? You have to bring it to the practical voltage source. So again this has to be again converted back into the practical voltage source. So we know voltage source, how we can do. So the V3, the voltage from this source will be equal to I into R. So that I is 2 and R is 6. So polarity will be upwards, positive will be upwards, and this followed by a resistance 6 ohms between the terminal A and B. So this, what is the value? It will be 12 volts. Okay. So this is the resultant answer for this question or numerical. So we'll go to the next problem. Okay, so here you have to identify some elements which are not required. I have already mentioned it, but still I will explain. So as per the redundant element, so the resistors connected in parallel with the voltage source will become redundant, and resistors connected in series with the current source will also become redundant. Okay, so after removing the redundant elements in the network, the resultant network will be 2 ohms followed by 10 volts, 5 ohms, 10 amps. This has to be removed. This is the reduced network from this to this. Okay, the question says again you have to convert back into a single source. Okay, either it can be, they have not mentioned what is the whether you have to convert back into voltage source or current source. You can retain both, or you can choose any one of the source to be retained at the end. Okay, so here you see, so this is a practical current source, right? And this is also a practical voltage source. Okay, and this also practical current source. So we can reduce at a time, but since we are learning for the first time, so we'll go by step. So we have terminal A. Okay, so first I will convert this one into a voltage source. Okay, so for that I will retain this as it is, 2 ohms, 10 volts. Okay, this I will retain as it is. This one I will convert into a practical voltage source. Okay, so voltage here it is connected with 24 volts in series with the 4 ohms. This is B. Again I will try to connect this one. Okay, so we have, so again I will convert this source into a current source. So for the current source, V by R, so you have 5 amps current source 2 amps, 2 ohms resistor, then you have 5 ohms resistor, then you have 10 ohms current source. See, this 5 amps and 10 amps current sources will have the same polarity or same direction. We can add up. Okay, so when we add up, this 2 will become 15 amps. Okay, and this resistor which is in parallel, we can calculate that as R1 R2 by R1 plus R2 to get the equivalent resistance. Okay, so R equivalent from this will be equal to 2 into 5 by 2 plus 5. Okay, so it will be around 10 by 7. Okay, so this 10 by 7 resistor will be connected across the 15 amps. Okay, and it is followed by a 24 volts. So I will erase this part. So resultant current source is 15 amps, then 10 by 7 ohms, then you have a voltage source 24 volts followed by 4 ohms between the terminal A and B. Again you change into a voltage source. This voltage source will be equal to, so this will be equal to 15 into 10 by 7 volts. Okay, followed by 10 by 7 ohms to the terminal A. Okay, and you have 24 volts followed by 4 ohms. Okay, so resultant will be 10 by 7 plus 4 ohms. Okay, then 24 plus so this is the single voltage source. Okay, this can also be written into the current source as well. Okay, so we'll do more and more problems in the next lecture series. Thank you.